Here we're going to apply reduction of order to this difference equation here. So x squared y double prime minus 3xy prime plus 3y equals 0. The first homogeneous solution we're given is y1 equals x. And this is actually an example of a Cauchy Euler equation. You can see later on. But we're going to just apply reduction of order to this. All right, so first thing to do is we're going to guess that the second homogeneous solution, y2, is equal to some function v of x times y1, which I'll just write as v times x. All right, then we go through, take two derivatives, plug it into the original ODE, and then try to solve for v. All right, so y2 prime is going to equal, well, it's going to be v prime times x plus just v times 1. Right, then rewriting that a little bit, I think I will put the, whatever, v prime x plus v. All right, then next up, find the second derivative. So we have y2 double prime. All right, well that's going to be, I've got a v prime and an x, so it's going to be v double prime x plus v prime times 1. Okay, that's this bit, and then I have another plus v prime. All right. If I can simplify that a little bit, let's see here, I have v double prime x. I have a v prime plus a v prime, so plus 2v prime. That's it. All right, now we're going to plug it into the original ODE. So we're going to have x squared times y2 double prime minus 3x times y2 prime plus 3y2. That all has to equal 0. So let's see here, I have x squared times v double prime x plus 2v prime, all right, minus 3x times y2 prime, which is vx prime, sorry, v prime x plus v, and I've got a plus 3 times y2, which is just v times x, and that all has to equal 0. All right, so let's multiply this out. I think I'm going to start putting the x's in front of the v's. So we're going to have x cubed v double prime. I've got a 2 plus 2 x squared v prime. Got a minus 3 x squared v prime minus 3x v, yeah, plus 3 x v equals 0. All right, but let's take a look here. So x cubed v double prime will stick around. I've got 2x squared v prime minus 3x squared v prime, so it's going to be a minus x squared v prime. All right, and then I've got minus 3xv plus 3xv, so it cancels, so I end up with 0. And now we have a simpler differential equation to solve. So let's go ahead and try and solve that. So let's see, if I take v double prime here, let's simplify it if we can. So we have, if I divide everything by x cubed, I get v double prime minus, okay, x squared over x cubed, that's 1 over x, times v prime equals 0. Okay, that doesn't look a whole lot better, but it actually is. So the reason this method is called reduction of order, and it shows up a lot better in this example, is, right, we started with a second order differential equation, hint order, right? So I have y double prime, I had y prime, and I had y. I still have a second order differential equation, it's just now for v, but it's just v prime, sorry, it's just v double prime and v prime. There is no v term. And so really, this is like a first order ODE. So to emphasize that, we're going to say that w, this new function of x, is going to be v prime of x. All right, if that's the case, then we're going to have w prime is equal to v double prime. And if I put that into the differential equation we have w prime minus 1 over x times w equals 0. And now this really is a first order differential equation. and we can actually use some of the methods we know to solve it. And so the method we're going to use is actually, let's use integrating factor. All right, so integrating factor, we have to figure out, right, the mu of x here. So we have our function here, right? We have 1 times w prime minus 1 over x times w. So our integrating factor, mu of x, is e to the indefinite integral of this piece in front of the w, the negative 1 over x dx. All right, well, if we compute that, that ends up being, let's see, so u of x equals, okay, I have e, integral of negative 1 over x, that's actually the negative natural log absolute value of x. Yeah, got that right. But then I can take that negative, I can put it inside, so that's really e to the natural log absolute value of x to the negative 1. It ends up being just x to the negative 1. We can get rid of the absolute value as usual. So we're going to multiply the whole thing by 1 over x, and that's going to make it integrable. So we'll have 1 over x times w prime minus 1 over x squared times w equals 0. So we should be able to collapse this into a reverse product rule, and I'm pretty sure we can. So that leads us to 1 over x w, the whole thing prime, equals 0. And that does make sense. So if I have 1 over x times the w part prime, that's the 1 over x times w prime. If I take the derivative 1 over x, well, it's x to the negative 1. You pop down a negative 1, so there's the negative. And then x to the negative 1 minus 1, we get x to the negative 2, so that's the negative 1 over x squared. Right, but now we can integrate both sides. So integral of 1 over x w prime dx equals integral of 0 dx. Okay, well that leads to just 1 over x w equals a constant. All right, well then w is equal to c times x, but remember w was v prime, so we actually have v prime equals c times x. So then one more integral, we get integral of v prime dx equals integral cx dx, and that leads us to v of x is equal to cx squared over 2 plus d. All right, and so now we have cx squared over 2 plus d, and we're going to figure out what y2 was. So y2 was supposed to be v of x times y1. Well, that ends up being, let's see, what do I have here? V of x was constant times over 2 times x squared plus another constant times x. And if we take out the unique thing here, so if we multiply that out, it ends up being c over 2 x cubed plus dx. And so the new unique thing we're going to pop out of there is actually that x cubed term. So we're going to choose, I'll put it up here, I ran out of room, so choose that y2 is the function x cubed, and that's the second homogeneous solution.